Okay, good afternoon. Last class we discussed about some force transducers. Initially, we talked about how the balances can be used for measurement of forces. We discussed a few of the proving ring type force measuring transducers, and we had just started off with strain gauge. Initially, we discussed about what is the principle of strain gauge, and just to recollect, strain gauge is a resistance wire which, when subjected to elongation, its resistance increases. When its length reduces, its resistance also reduces. This property of the conducting wire is utilized for measurement of strain, and as we all know, as a mechanical engineer, stress is proportional to strain. When I can measure strain, I can always measure stress, provided I know modulus of elasticity. So once I know stress, provided I know the cross-sectional area of the member, from the stress value, knowing the cross-sectional area, I can always find out the force. So this is how the strain gauge can be used for measurement of strain, first of all, can be used for measurement of stress, and can be used for measurement of force as well. So strain gauge as a force transducer is widely used. This is what we discussed. So it is essentially either a foil type strain gauge, wherein foil means a sheet. So it is in the form of a thin plate. It's called as a foil, and it is sandwiched between these two backing papers. So this is a plastic film, laminated film, which is electrically non-conductive. So the strain gauge is sandwiched between these two papers, and the reason for sandwiching these strain gauges is very simple. If I take a strain gauge, it is very difficult for me to handle it because it is very thin and fragile. So by using these backing papers, I can hold the strain gauge assembly, so to say, very easily. And it becomes very easy for me to mount these strain gauges on the specimen also. The bare strain gauges being very fragile and thin, uh, directly I cannot mount them on the specimen material. So that's why these backing plates or backing sheet, uh, these are used for holding, or rather sandwiching the strain gauge between them. Okay, so when a wire is stressed longitudinally, resistance undergoes a change. Passing a small amount of current through such wire will thus help measure voltage change. As I discussed in the last class also, as the length increases, let us say resistance increases, so delta L, corresponding to delta L, I'll have delta R, and I'll have a balancing circuitry, potentiometric circuitry outside. And this delta R can be converted into delta V by using a potentiometric circuit. So I can measure this strain in terms of resistance change and in terms of voltage change. And as I discussed earlier, this strain can always be converted into stress by knowing the Young's modulus of elasticity. By knowing the cross-sectional area, I can always convert this strain into the applied force. So force can be correlated with directly with this R, first of all. So this force can be correlated with stress. Stress can be correlated with strain. Strain is correlated with delta L, and as resistance of the conducting wire is proportional to length, as length increases, resistance also increases, and as the resistance increases, the potential drop across this resistance also increases. So I'll be having increase in voltage. So this is how the strain gauge principle works. The sensing element of strain gauge is made of, there are various alloys those are used, copper, nickel, alloy foil. The alloy foil has a rate of resistance change proportional to strain with a certain constant. Let us go further. What are the types of strain gauges? In fact, there are a number of types of strain gauges. We'll be discussing only few types of strain gauges. There are, whatever we are going to study are called as bonded electrical resistance type strain gauges. So there are unbonded type also. Simple wire strain gauges are also there. Tension wire is used. There are semiconductor strain gauges, thin film strain gauges, diffused semiconductor strain gauges. So this is bonded resistance strain gauge. That is what we are going to study now. The selection criteria, which strain gauge is to be selected, depends on the nature of strain, and it also depends on operating temperature and stability requirement. We'll discuss about this a bit. And as you can see on the right image, the single foil type strain gauge, right? So the width can vary from 5 millimeter. These are exaggerated figures. The width varies from 5 millimeter. 5 millimeter, just remember, 5 millimeter, that is 0.5 centimeter. And it varies, the length varies from, it also varies from 5 millimeter to maybe 25 millimeter. So these are very small strain gauges. So this is our regular foil type strain gauge. These are the 2-element foil type strain gauges. These are star type strain gauges. This is called as diaphragm. These are used for pressure measurement. The diaphragm that which is subjected to pressure will get deflected, and I'll be having these strain gauges which are mounted on the diaphragm, which sense the strain, and that strain can be correlated with pressure change. Like that. Now there are some customized strain gauges also. If we have a turbine rotor blade or a windmill blade, and if I want to measure the stresses induced on that windmill blade, so what I can do is I can customize my strain gauge. So I can ask the manufacturer about my loading requirement, my length requirement, and he can build a strain gauge, multiple element strain gauge assembly for you. So this is also one type of diaphragm type strain gauges. There are some rosettes also, those can be seen. There are delta rosettes, star rosettes. These are the 2-element rosettes where I want to measure the biaxial strain and biaxial stress. So I use this 2-element rectangular rosettes. So these we'll see later on. Earlier we had this subject as an elective subject in our Solapur University syllabus called as experimental stress analysis. So we have a full-fledged stress analysis laboratory. We have some polariscope devices which you can always, once you come to college, you can always visit the lab. And we have very good collection of strain gauges as well. In fact, a few years back, I had built one load cell which was able to measure the tool forces. So it is called as lathe tool dynamometer. It can measure the X component of force, Y component of force, and Z component of force. That is cutting force, forward field force, and radial field force. All the 3 forces that strain gauge load cell can measure. So one can take a project also based on strain gauges. Now coming to the selection criteria, I'll be using this strain gauge assembly for measurement of forces, let us say. If you visit our IC engine lab, I don't know whether last year you must have done some experiments on IC engine lab. So you have one dynamometer, AD current type dynamometer, and there are some probably hydraulic dynamometers also. So the AD current dynamometer, there is one S type of strain gauge assembly which measures the forces. So once you come to college, I can show you that strain gauge load cell. But the point is, when the operating temperature is hostile, in a sense, if the operating temperatures are higher, the strain gauge have a bit of problem, because as we have seen the expression in the last slide, R is equal to rho into L by A. We looked only upon the length change part, but because of temperature, the resistivity rho also changes. So because of length also R changes, because of rho also if R is changing, then it becomes difficult to measure whether the change in resistance is only because of change in length or it is also because of temperature effects also. So my readings, my outputs would be faulty or error prone. So I need to select appropriate strain gauges for particular applications. Now, second selection criteria is nature of strain. Now, whether whatever we have studied in design of elements, machine design 1 and machine design 2, in most of the cases, we have seen uniaxial stress system and uniaxial strain system. So there is a beam and I'm subjecting it to bending, so to say. So only along the length of the beam, I have the stresses and strains induced. So that is a simple uniaxial stress case. Or there is a shaft which is subjected to, or there is a bar which is subjected to tension or compression. So that is also one case, typical case of uniaxial stress system. But if you see the practical cases, suppose I have got automobile. If you studied automobile, you have a suspension system bracket is there, and it has got a complex geometry, and it has got complicated loading also. So there I don't expect that there will be uniaxial stress system. So there can be biaxial stress system or there can be triaxial stress system. What is the meaning of this biaxial stress system and triaxial stress system? Earlier we used to have only sigma as one stress component. Now when I go into detailed studies of stress analysis and to be uh, on realistic side, what happens is the actual stress components, just to go into a bit more details, I have sigma x and sigma y. And if I want to go further into details, along x direction, how much is the normal stress, along y direction, how much is the normal stress, along z direction, how much is the normal stress. If I want to measure all the three stress components, normal stress components, I need to go in for, once again, specialized type of strain gauges. Yes, the strain gauges for measurement of all the three components of stresses and strains are available in market. And in fact, in most of the research laboratories, those are used. Every year I used to take final year students to, there is one wonderful experimental stress analysis laboratory at Khadakwasla, Pune. It is called as Central Water and Power Research Institute, it's a Power Research Station, CWPRS, Central Water and Power Research Station. So it's a central government organization wherein uh, all the dam models are available. And in fact, there is a wonderful photoelastic model for a Koina dam also. And whatever penstocks are there which supply water from high altitude to drive the hydraulic turbines, they have a setup to measure the circumferential stresses those are induced along the penstock, that is along the pipe. So a wonderful stress analysis laboratory is there. So there the stress components are different. You have circumferential stress or hoop stress components, those are to be measured. So there my selection of the strain gauges would be different. And stability requirement. Stability in a sense, when I talk about stability, it is always a dynamic stability. Suppose I want to measure the stresses and strains induced in a connecting rod, let us say. Now, connecting rod is constantly moving, so it is subjected to fluctuating loads all the time. So there are fatigue stresses, so to say. It might fail due to fatigue. So if I want to measure the stresses induced in the connecting rod, what I do is I measure strains first and I convert those strains into stresses. Well, there is a sophisticated conversion circuitry available. So the setups are, customized setups are always available. But there I'm subjecting the strain gauges to dynamic stresses or dynamic strains, or the strains constantly changing with time. Now, in such cases, whatever we have studied initially as the transducer characteristics, we studied some static performance characteristics and dynamic performance characteristics as well. So the strain gauges, those I'm going to select for measurement of strains in the connecting rod. Those need to have uh, dynamic stability also, and its speed of response should also be better. And the output shown by the strain gauge circuitry in terms of voltage change should be in phase with the strain change. So probably you're getting what I'm telling you. There should not be any time lag as such, because the failure has occurred there, and thereafter I'm sensing that there is so much of strain. It should not happen in such a way. The strain gauges should have better static and dynamic response characteristics as well. So based on these criteria, I select appropriate strain gauges for my force measurement applications. Let us go a bit further. We'll see bonded strain gauge. As I discussed just now, this is a very small foil type strain gauge. The sketch is shown here. When this is mounted, it is mounted on the, see, on a beam it is mounted. There is a specific mounting procedure which we'll be studying later on. That it is mounted so that it becomes integral part of that specimen. Okay, so whatever changes those are taking place in the specimen material, let it be a shaft, let it be a cylinder, let it be a beam, whatever changes those are taking place on those specimens, the same will be reflected in the strain gauge. The bonding technique also has to be appropriate. So whatever stresses are induced in the specimen and whatever strains are induced on the specimen, of course these are the surface strains, those should be transmitted to this strain gauge. So the strain gauge, when subjected to tensile strains, it will elongate, and when it is subjected to compressive strain, its length will reduce. And at the same time, as I said, I have a beam like this. I have a beam, cantilever beam, which is supported at this end, let us say, and I have mounted this strain gauge. So the width of the beam, I keep it in such a way that when I load this cantilever beam, see, perpendicular to the line of vision. See, by point, whatever pointer is there, perpendicular to that pointer, I am applying load, let us say. And I presume that, and for all practical purposes, we treat it as a uniaxial loading system. And these strain gauges, being smaller in width, they don't sense these lateral strains. Okay. So gauges insensitive to lateral forces and lateral strains. Even though theoretically I say like that, practically there will be some error because of lateral strain. So if you study in depth, we'll be considering one small component of Poisson's ratio mu into delta R also in my calculations when I'm going for exact calculations of strains. Okay, moving further, to measure the strain requires accurate measurement of very small changes in resistance. As you can see, whatever I told in the last slide, this delta R that I get corresponding to this delta L, actually it is very small, because delta L itself is small. Delta L itself is very small. So delta L, when the delta L is very small, it is clarified by taking a simple example. Suppose a test specimen undergoes a strain of 500 into 10 to the power minus 6. Now this is actually, strain is a quantity, it does not have any units as such, because it is the ratio of change in length by original length. So meter, millimeter gets cancelled. So it's a dimensionless or unitless quantity. But because these values are epsilon or strain values are very small, the change in length to original length is very small. Just to take as an example, this is this 500 into 10 to the power minus 6. So if I rearrange this, it will be 500 divided by 10 to the power 6, isn't it? Are you following me? This 500 into 10 to the power is minus 6. Just if I take this 10 to the power minus 6 to the denominator, It is actually in the denominator. What happens is it becomes 500 upon 10 to the power 6, which is equal to delta L upon L. Please be attentive. So 500 upon 10 to the power 6 is equal to delta L upon L. So what is the meaning? If the original length is 10 to the power 6 units, if the original length, which is in the denominator, is 10 to the power 6, my change in length will be equal to 500 units. So you can understand how small this strain is. It is 500 upon 10 to the power 6. It's a very small fraction. So it is designated as this 500 into 10 to the power minus 6 is designated as 500 microstrain or 500 mu strain. So mu corresponds to 10 to the power minus 6. So it is not a unit, but it is a method of representation of strain gauge. So just now I told you the strain value is very small. Now we'll understand slowly this gauge factor of a strain gauge. Gauge factor of a strain gauge is delta R upon R. Now this is to be corrected. Delta R upon R divided by epsilon. It's not mu. It needs to be corrected. It's delta R upon epsilon. Gauge factor is the characteristic of a strain gauge. It is a strain gauge factor. Strain gauge factor, it is designated by K, is equal to delta R upon this needs to be epsilon. Delta R upon epsilon. Okay. Delta R upon epsilon. What is epsilon? Epsilon is strain. Now corresponding to epsilon, I'll be getting some change in resistance. Now the changing the original resistance, let us say it is 120 ohm. I can always find out how much will be the change in resistance. So just be attentive a bit. Gauge factor K is equal to dr by R upon epsilon. As I said repeatedly, this is not mu, it is epsilon. So gauge factor K is equal to delta R or dr by R upon epsilon. Now epsilon is 500 into 10 to the power minus 6 at the denominator. And let us say if the gauge factor of a given strain gauge is 2. Okay, so on the right hand side I'll have 2 and forget about this. Denominator I'll have 500 into 10 to the power minus 6. And if the original resistance is 120, this R is 120, I can find out how much will be. You can also calculate how much will be dr corresponding to strain of 500 microstrain. It comes out to be 0.12 ohm. When the original resistance is 120 ohm corresponding to 500 microstrain of strain epsilon, I'll be getting such a small resistance. So by using potentiometric circuit, it becomes very difficult for me to measure this small change in resistance. I can measure, but the thing is that the error should be very huge. So what I do is I go in for a Wheatstone bridge circuit. Now the Wheatstone bridge, it is also called as a balancing circuit. The Wheatstone bridge circuit helps me in measurement of small resistance change also without much error. Now what is this Wheatstone bridge circuit? Those today we'll just initialize the discussion. Next class we'll discuss it further in details. If you see here, the Wheatstone bridge circuit has got 4 arms. We have studied it right from 10th standard, 12th standard. We have studied Wheatstone bridge. Okay, so it has 4 arms. It is forming a bridge. So R1, R2, R3, and R4. So these are the 4 resistances which are connected. Let us call it as A, B, C, and D. So A, B, C, D is a bridge that I have. What I do is across A and C, I give the input voltage. Across A and C, I provide the input voltage. Normally, I give input voltage of around 6 volts DC. This is the input voltage I give. And across B and D, I take the output voltage. And this output voltage is designated by dV or small v. the methods of designation differ. So I give some input voltage and I see the output voltage. If you remember your college days or school days, this Wheatstone bridge was used to find out or to measure the unknown resistance. What we did then, I had initially all the four resistances of same value. So when there is initial balance, so condition for initial balance is R1 by R2 is equal to R3 by R4. You remember, R1 by R2 is equal to R3 by R4. If R1, R2, R3, R4 are same, 300 ohm each, what will happen? The bridge will be balanced. When the bridge is balanced, what happens is across B and D, there will not be any voltage. Why there will not be any voltage? Because B and D will be at same potential. If the B and D are at different potential, then only there will be voltage across, output voltage across B and D. What does that mean? There is no current as the potential is same, as the potential at B and potential at D are same. There will not be any branch current flowing across B and D. That's what we did during our college days, if you remember. I used to have one galvanometer in between. The galvanometer is nothing but ammeter. It measures the current. So what we did, we measured the current across B and D. And I varied. What you did was R1 and R2 you kept same. And let us say R4 was your unknown resistance. And R3 was my variable resistance. If you recollect, R1 and R2 same. R3 is a variable rheostat I use, and R4 was my unknown resistance, if you remember. So what you did, you varied this resistance, variable resistance, in such a way that this galvanometer reads 0. It shows null reading. So what you did, when it shows null reading, what does that mean? When the ammeter shows 0 reading across B and D, what does that mean? There is no current flowing across B and D. When there will not be any current flowing across B and D? When B and D are at same potential. When B and D are at same potential, we say the bridge is balanced. So there is no output voltage in that case, isn't it? So whatever, so using R1 by R2 is equal to R3 by R4. R4 was my unknown resistance. R3 was the known variable resistance you had. So by using R1 by R2 is equal to R3 by R4, I know all the three values. I could find out what is R4. That is what we did during our college days. This is a simple resistance type Wheatstone bridge circuit, okay, which is used. Well, whatever we discussed just now is called as a null balance method. So null balance method, I varied the resistance in such a way that potential at B and D are same and there is no current flowing across that. So the current across B and D was made to be 0 or null. So that's why it is called as a null balance type Wheatstone bridge. And there is the second type that is called as deflection type. I don't use any ammeter in between. What I do is across B and D, I simply measure the output voltage. So if I use a voltmeter here, it starts deflecting when there is disturbance in the bridge. Okay, so that is called as deflection type of bridge, Wheatstone bridge. We use mostly deflection type of bridge for our strain gauge circuit. If you have understood a bit about this Wheatstone bridge, wherein I am using all the four resistances, just let us come to this usage of Wheatstone bridge for strain gauge. As you can see in the figure, instead of this unknown resistance, what I have done, I have connected the strain gauge across one of the arms of the Wheatstone bridge. Okay, so one of the arms of the Wheatstone bridge which is subjected to strains. As it is subjected to strains, it is subjected to change in length, and as it is subjected to change in length, it is subjected to change in resistance. So this branch resistance would be changing. So my objective is to measure this delta R, which is corresponding to epsilon. Okay, so that is needed to be measured. So it is measured by using this Wheatstone bridge circuitry. We'll see what are the equations related to. This is called as a single arm bridge, because there are 4 arms of this Wheatstone bridge. Out of the 4 arms, only one arm I have made it as an active strain gauge arm. It is called as a one arm bridge. We'll see the details of this single arm bridge strain gauge Wheatstone bridge circuitry in the next class in details. As I said, as the specimen is subjected to loading, it is subjected to stresses, it is subjected to strains, and as the strain gauge is mounted on the specimen beam, the strain gauge is also subjected to strain. As the strain gauge is subjected to strain, it is subjected to change in length, and because of the change in length, its resistance R changes, and as the R changes, my condition for initial balance, this is R1 by R2 is equal to R3 by R4, gets disturbed. So as the condition for balance gets disturbed across these two terminals, this is the supply volt 6 volt I am giving, and across these two branch points I'll be measuring the output voltage, right? That voltage delta V can be correlated with delta R of the strain gauge, and that delta R can be correlated with strain, and that strain can be correlated with stress, and that stress can be correlated with force applied. Hope you have gone a bit faster. We can repeat if you require. Next class we'll discuss this in further details. The Wheatstone bridge is an electric circuit for detection of very small resistance change. It is therefore used to measure resistance changes of a strain gauge. The strain gauge is connected in place of resistance R4 in the circuit. When the gauge undergoes strain and initiates a resistance change delta R, the bridge outputs a corresponding voltage. Okay, so this is how the Wheatstone bridge used to measure the strain gauge change in resistance. I think we should stop for today. Thanks for watching. If you have any questions, just post those questions on my WhatsApp number, or you can call me anytime if you have any difficulty. So we shall stop for today. Thank you very much for watching. Have a nice day. Thank you.